All right, I'm going to be going through question 5 with you. So I'm just going to read out the question. Two racing cars, A and B, are at rest alongside each other at a point O on the straight horizontal test track. The masses of A is 1,200 kilograms. The engine of A produces a constant driving force of 4,500 newtons. When A arrives at point P, its speed is 25 meters per second. The distance OP is d meters. The work done against the resistance force experienced by A between O and P is 75,000 joules. Show that D is equal to 100 meters. Okay, so what I'm going to be using to answer this question is the work energy principle, which states the sum of the work, which is Fs, would be equal to the change in the kinetic energy. So it's a half mv squared minus a half mu squared. Okay, so now this sum of the work here, that's going to be the driving force in this direction and then the resistance force in that direction. So that's how I'm going to state. I'm going to say Fs in the driving force minus Fs in the resistance force is equal to a half mv squared minus a half mu squared. Okay, so we know what the force is in the driving direction. They told us here that we have a driving force of 4,500 newtons. So 4,500. The displacement, we don't know, so I'm going to call that D minus. Now with this one here, the resistance, they've told us here that we have or the work done against the resistance force experienced by A between O and P is 75,000 joules. So that is your Fs, that is the work. So this is minus 75,000 equals a half. The mass is 1,200, and they told us that the velocity was 25 meters per second minus a half. Again, the mass is 1,200, and our initial velocity is 0 because they start from rest. Okay, so that's just going to give us 4,500 D equals, work this out over here on the calculator, and we should get 375,000. Take this to this side, plus 75,000. Simplify, and we get 450,000. Divide by the 4,500, and we get D is equal to 100 meters as required. Okay, then question B goes on to say car B starts off at the same instant as car A. The two cars arrive at P simultaneously and with the same speed. The engine of B produces a driving force of 3,200 newtons, and the car experiences a constant resistance to motion of 1,200 newtons. Find the mass of B. So once again, I'm going to be using the work energy principle. So sum of the work is equal to the change in kinetic energy. Okay, so again, I'm going to break this down just like I broke this one down. The work done in the driving force and then the work done in the resistance force. So Fs in the driving force minus Fs in the resistance force equals a half mv squared minus a half mu squared. Okay, so the force in the driving direction, they told us, is 3,200. So we get here 3,200 multiplied by the displacement is 100 minus the resistance force, they told us, is 1,200 multiplied by the displacement, which is 100, equals a half. We don't know what the mass is. Now, the velocity they said is the same as car A when they get to this point P. So the velocity of car A was 25 meters per second. So this is 25 squared minus a half m, and the initial velocity is 0. Okay, so if we work out what this is on the calculator, we get 200,000 equals, then we've got 25 squared over 2, which is 625 over 2, multiplied by the mass. We can divide by the 625 over 2, and we get the mass is equal to 640 kilograms. Okay, then question C. Find the steady speed which B can maintain when its engine is working at the same rate as it is at P. So just a quick thing there, when they're talking about steady speed, this implies that acceleration is equal to 0 because there's no change in your velocity. Okay, it's a steady velocity or steady speed. What I'm going to do next is I'm going to work out the rate at which the engine works, because they're talking about here the same rate. Okay, and when we're talking about the rate at which an engine works, that is power. So power is equal to F times V. Okay, so this is the rate at which an engine works. All right, so we can work out what the power is of car B. So power is equal to, now we have a driving force of 3,200 multiplied by, and our velocity is 25. So we get power to be 80,000 joules. Okay, so that is at point P. The rate at which the engine works at P is 80,000 joules. So I just want to say here at P. All right. But the question is, we want to work out what speed must this car travel at in order to maintain this power from P onwards. Okay. So I'm going to use Newton's second law, which is F is equal to MA, and this is the resultant force, so it's going to be F in the driving direction minus F in the resistance direction equals MA. Now, this one we know what it is. It's 1,200, okay, from the previous question. But this F over here, I want to now work out what must this driving force be in order to maintain this amount of power. So what I'm going to do is I'm just going to rearrange this formula over here. I know that my power that I need to maintain is the 80,000. So we have 80,000 equals F times V. Okay, I'm going to divide through by the V, and this is the driving force that we have to maintain in order to keep this power of 80,000. Okay, so that is what I'm going to replace this one with. So we're going to get 80,000 over V minus the resistance, which is the 1,200, equals, now the mass, we don't really need to know what the mass is. The acceleration is 0. Okay, rearrange this. So I'm just going to multiply up by V, and we get 1,200 V equals 80,000. And then divide through by the 1,200, and we get V is equal to 66,7 meters per second. In other words, this is the speed that which B must maintain in order to have a power output of 80,000 from P onwards. Okay. I'm going on to question 6. I'll just bring it up here so we can see what's going on. Okay, a particle starts from point O and moves in a straight line. The velocity v meters per second of the particle at time t seconds after leaving O is given by this function here. V is equal to k, 3t squared minus 2t cubed, where k is a constant. Question A. Verify that the particle returns to O when t is equal to 2. So in other words, what I'm going to do here to show that something returns to its same spot is if the displacement is 0. And because we are given a velocity function, I'm going to be using this. So if we're working in this direction, we're going to be finding the derivative. In this direction, we're going to be finding the integral with respect to time. So I am going to, because we've got the velocity function and I want to find displacement, I'm going to be integrating this. So if we take the integral of v dt, that means I must integrate this side with respect to t. So the integral of k, 3t squared minus 2t cubed dt. Now, before I integrate, I'm just going to multiply this 2 inside here just to make it easier for us to integrate. So integral of 3k t squared minus 2k t cubed dt. All right. If I integrate velocity, I'm going to get displacement. And if we integrate this term over here, that's going to become t cubed. So we'll get 3 over 3k t cubed minus, that's going to be t to the 4. So that's going to be 2 over 4k t to the 4 plus some constant of integration. Okay, so in order to find this constant of integration, we need some initial conditions. So I know that when time is equal to 0, our displacement will be equal to 0. So I'm going to plug those initials in here, and we get 0 is equal to, because our s is 0. If t is 0, this term falls away. Again, t is 0, this term falls away, and we're just left with the c. So that means that c is equal to 0. I'm going to plug that back into here, and then just simplify our coefficients there. So we get s is equal to, that's going to give us 1, and we get k t cubed minus, that's going to give us a half, k t to the power 4. So now that I have a function for displacement, and what I'm going to do now is I'm going to plug in when time is 2 into here, and if we get 0, that means our displacement is 0. That means that this particle has returned back to its original position. So we get s is equal to k times 2 cubed minus a half k 2 to the power 4. That gives us 8k minus, that's 16 divided by 2 is 8k, which gives us 0 meters. So therefore, that means that this particle has returned back to O. All right, question B. Question B is saying, it is given that the acceleration of the particle is negative 13.5 meters per second squared. For the positive value of t, so we know that t is some positive value, at which the velocity is equal to 0. So we've got two things here that we need to find. First of all, find k, and hence find the total distance traveled in the first 2 seconds of motion. So the first thing I'm going to do is I'm going to find out what is this value of k over here. So I'm going to be using this information over here first. They told us that velocity is 0, and I'm going to find out the t value that will give us a velocity of 0. So we have a function for our velocity. It's over here, and I'm just going to be using this one here, because that's the original. So we've got v is equal to k, 3t squared minus 2t cubed. Make our velocity 0. And I'm going to find the t value that gives us that velocity 0. So because k is some constant, that means that just this bracket will be equal to 0. So we get 3t squared minus 2t cubed equals to 0. Take out a common factor of t squared, and we're left with 3 minus 2t is equal to 0. So that means that t is equal to 0, or t is equal to 3/2 seconds. Okay. So that's the one that we're looking for there, because t must be greater than 0. So that is our solution there. Okay. So we've got the one bit of the question, which is, oh, we haven't got anything yet. So I've got the when t is 0. So I'm going to be using now the second bit of information, which is this acceleration over here. And we've got a velocity function. Okay, so I know in order to find the acceleration, I need to differentiate the velocity. So acceleration is equal to the derivative of velocity. Okay, so that means that acceleration is equal to, and all I'm going to be doing is I'm going to be differentiating this one over here. Okay, it's exactly the same as that. It's just easier because we've multiplied in the k. All right, so we get 6kt minus 6kt squared. Okay, but I know what the acceleration is. The acceleration is negative 13.5 when t is 3/2. So if I make my acceleration negative 13.5 equals 6k, time is 3/2 minus 6k 3/2 squared. So negative 13.5 is equal to, that is going to give us 9k minus 27/4. So that's going to give us 27/2. Okay. Right, so just get these two together and we get minus 13.5 is equal to minus 9/2k. Divide through by the minus 9/2, and we get k is equal to 3. So we've got the one bit of information that they wanted us to find, which was the k. And what we need to do now is we need to now find the total distance traveled in the first 2 seconds. So I'm going to back substitute this into this one over here. Okay, just so that we've got a nice velocity function. So we've got that velocity is now equal to 9t squared minus 6t cubed. And I want to find now the total distance in the first 2 seconds. So what I'm going to do is I'm going to find the integral of this, because if we integrate this, we find displacement. However, I've got 2 different time sectors here that I need to look at. I need to look at between 0 and 1.5, because that's going up and then it stops. That's what we worked out over here. And then it's going to start falling back down again, and it's only going to fall for half a second, because this goes up to 1.5, and we only want to work up to the first 2 seconds. So I'm going to be looking at when t is between 0 and 1.5 first. So we're going to take the integral of v dt of this thing here, which is going to be equal to the integral from 0 to 1.5 of 9t squared minus 6t cubed dt. So that's going to give us the displacement upwards. And if we integrate this, we get 9/3 t cubed minus 6/4 t to the 4 from 0 to 1.5. Okay. If we put that on the calculator, we should get 81/32 meters. Okay. Then I am now going to do exactly the same thing, but from 1.5 up to 2. Okay, so the integral of v dt is equal to the integral from 1.5 up to 2 of 9t squared minus 6t cubed dt. Okay, so now this is the displacement downwards. And we're going to get 9 over 3 t cubed minus 6 over 4 t to the 4 from 1.5 up to 2. Okay, and this I'm going to be doing on the calculator. So we've got the integral of 9 t squared minus 6 t cubed from 1.5 up to 2. And we get minus 81 over 32. Now, just remember that this is displacement, and they are all talking about the distance, the total distance. So what I need to do now is total distance would be equal to 81 over 32 plus 81 over 32. Just remember that this is displacement. The negative is telling us it's going in the opposite direction. So distance is just going to be the positive value of that. And we get 81 over 16. And if we put that into decimal, we get 5,0625 meters. So that is the total distance traveled. We are now going on to question 7. Read it out. Two particles A and B of mass of 0.4 kilograms and 0.2 kilograms respectively are moving down the same line of greatest slope of a smooth plane. The plane is inclined at 30 degrees to the horizontal, and A is higher up the plane than B. When the particles collide, the speeds of A and B are 3 meters per second and 2 meters per second, respectively. In the collision between the particles, the speed of A is reduced to 2.5 meters per second. Question A. Find the speed of B immediately after the collision. So what I'm going to do here is conservation of energy. So in other words, momentum before must be equal to the momentum after the collision. So we have m1u1 plus m2u2 would be equal to m1v1 plus m2v2. And I'm using this form because they don't coalesce. They don't become one object after the collision. They're still two separate bodies. Okay, so let's just substitute all these values in. So we know the mass of the first one is 0.4. The initial velocity was 3 for this one. Then the mass for object 2 was 0.2. The initial velocity for this one is 2 equals the mass of the first one is 0.4. Then the velocity after the collision is, for mass 1, is 2.5, plus the mass of the second object is 0.2, and the velocity we don't know. Okay, so if I put all of this on a calculator and take things to one side, we get 0.2v2 is equal to 3 over 5, and that will give us, if we divide by 0.2, we get v2 is equal to 3 meters per second. Okay, question B goes on to say, after the collision, when B has moved 1.6 meters down the plane from the point of collision, it hits a barrier and returns back up the same line of greater slope. B hits the barrier 0.4 seconds after the collision, and when it hits the barrier, its speed is reduced by 90%. the two particles collide again 0.44 seconds after their previous collision, and then coalesce on impact. In other words, they become one object or one mass. Show that the speed of B immediately after it hits the barrier is 0.5 meters per second. Then hence find the speed of the combined particle immediately after the second collision between A and B. So the first thing we're going to do is we are going to show that the velocity of B is 0.5 after it hits the barrier. So I'm just going to draw up a little picture here just to see what is going on. So we've got some kind of an inclined plane. We've got object B. It travels 1.6 meters down the slope. This is angled at 30 degrees. And then we have a mass of 0.2 kilograms. Okay, so what I want to do here is we want to find after it hits the barrier. Okay, so what I'm going to do first of all is I'm going to find out what the speed is when it hits the barrier. Okay, and then once I've got that, then I can work out the speed after it hits the barrier because they said it's reduced by 90%. Okay, so in order to find out what the speed is that it hits the barrier, I need some type of information. So if we look at SUVAT, we know what the displacement is. It's 1,6. The initial speed we know is 3. This is the one that I want to find out. Okay. And the time we don't know. They don't mention anything about time. So what I need to do first of all is I need to find acceleration somehow in order to use one of the SUVAT equations. So I'm going to, first of all, with newtons, we're going to say F is equal to ma. This would give me the acceleration of this body, okay? So the only force that's acting on this is it going down like this. So I'm going to break down the force of B into its components. So I am looking for this component over here, and that's 30 degrees. And we know what the weight would be here. The weight would be equal to m times g. So our m is 0,2 times 10. So we get 2 newtons. Okay. So this bit over here is 2 newtons. To find out what this is, it's going to be sine. So we know that this bit over here is going to be 2 sine 30 is equal to, we know what the mass is, it's 0,2 times by A. That means that A would be equal to 5 meters per second squared. So now I know what this is here. Okay, so this is the one that we want to find. So we use V squared is equal to U squared plus 2AS because it's the one without the T. Substitute these values in. V squared is equal to 3 squared plus 2 times 5 multiplied by 1.6. So we get V squared is equal to, put this on the calculator, and we get 25. Take the square root and we get V is equal to 5 meters per second. Now, I'm going to take this direction as positive. So I'm not interested in the negative root of this, just the positive root. So now we know what the speed is of B as it hits this barrier over here. So now to work out the speed after it hits the barrier, so speed of B after hitting barrier is going to be equal to, now it's 90%, it's reduced by 90%. So we're going to take the speed before and we're going to subtract 90% of that speed. And we get 0,5, okay? But remember, I took this direction as positive, so it's rebounded and it's going in this direction. So therefore, the velocity is going to be equal to negative 0.5 meters per second. It's in the opposite direction. Okay, so we've got that, which is the 0.5, and then the velocity would be negative 0.5. Now we're moving on to the second part of the question where it says, hence, find the speed of the combined particle immediately after the second collision between A and B. So what I need to do first is I need to find out what is the velocity of A after this time has gone. And they're talking about, I'll just read the sentence. They said the two particles collide again 0.44 seconds after their previous collision. So for A, we're going to use the Suvat equation. So S equals U equals V is equal to A is equal to, and T is equal to. So again, okay, so the time they have given to us this time, and it is 0.44. Okay, this is the one that we want. I know what the initial speed was. The initial speed was 2.5. Okay, so that was given in the question and we used it over here. 2.5 after the collision. So we know that the initial is 2.5. This we don't know. We don't know how far it's gone down. So I don't think we'd be able to find this. However, I could find the acceleration exactly the same way that I found the acceleration like this over here. Okay, so I'm just going to draw up a little picture for A. Again, 30 degrees. Here is A. We've got a mass of 0.4. And that's 30 degrees. So what I want to do is I want to find the acceleration in this direction. So again, we're going to say that F is equal to ma. So the force going in down in this direction now for A is going to be, the weight is going to be m times g. So we get 4 newtons. Okay, so that's going to be 4 sine 30. Equals, we know what the mass is, it's 0.4 times A. Work this out on the calculator and we should get that A is equal to 5. Okay, so now we're looking for the Suvat equation that excludes displacement, and that is V is equal to U plus AT. So V is equal to 2.5 plus the acceleration is 5 plus the time is 0.44. Plug that on the calculator and we get a velocity of 4,7 meters per second. Okay. Now, the same thing applies with B. I want to find out what the velocity is after all this time has gone. Okay. So, again, Suvat, S equals, U equals, V equals, A equals, and T is equal to. So again, we don't know how far this thing has traveled. We know what the initial speed is. The initial speed was, we worked that out over here, negative 0.5. Okay. And then the final velocity we don't know. The acceleration we do know, and that is 5. Okay. It's still acting down the slope, the acceleration. And now, here comes the tricky bit, the time, all right? So they said that these two particles collide 0.44 seconds after their previous collision, But it also says that B hits the barrier 0.4 seconds after the collision. So what I want to work out is the time it takes from hitting the barrier back up the slope as it hits A. So that's going to be that 0.44 minus the 0.4. So that total time for A minus the time that it takes to hit the barrier. Okay, and that gives us 0.04 seconds from the time that it leaves the barrier to it hits A again. All right, so the SUVAT equation that excludes displacement is going to be the same as this one. V is equal to U plus AT. So our initial velocity is negative 0.5 plus 5 plus the time 0.04. Plug that in the calculator and we get a velocity of negative 0.3 meters per second. Okay, so now what I have is I have the velocities of both A and B just before the collision. I have their masses, so that I can use conservation of momentum. So we get here mom before equals momentum after. M1 U1 plus M2 U2 is equal to. So here they're separate bodies, but however, after the collision, they become one. So this is just going to be MV. Okay, so the mass of A was 0.4. The velocity was 4.7 over here, plus the mass of B, 0.2. The velocity of B we calculated over here, negative 0.3, is equal to, now this is the combined masses, so 0.2 plus 0.4 is 0.6 V. Put this in the calculator and we get V is equal to 3.03 meters per second. So I think the trickiest bit was just this working out the time over there. All right.